Good morning, good afternoon, wherever you are. Thank you for being here with us at SnT again. So, as you can see behind me, there's the first speaker is already taking place. He's taking his seat. I will not start too early because we have a little bit of an introduction, and I want to make sure we are. The organizer told me we have to be very strict with the time, so I will be very strict with the time. So we'll wait a couple of minutes so that we can start on time. So yeah. So thank you for being at this PTS session. It's the second part of the PTS session that started on Wednesday morning. And so it's a few more presentations that will be about the work of the PTS. Here we will have this morning 3 presentations from colleagues from the International Data Center that are looking into the different technologies, radionuclide in particular, waveform technologies afterward, and then we'll finish with a fusion of technologies. So we'll have a good overview of what the IDC is actually doing and performing for its mission and also for the member state activities. I also would like to remind you that these presentations are not part of the voting system because it's for the PTS, but you can vote for best oral presentation and best posters. So please don't hesitate to do this. And what else should I tell you before we start? Everything is streamed, so if you have any questions, I will take, if we have time, if the speakers don't go too much over time, then we will take a couple of questions from the room, and we can also take questions from the online audience, or if you do not want to ask a question live, you can also type it on the app, and I will give it to the author if there is a bit of time. So with this, I will invite Dr. Gheddou to go to the podium and shortly present his work to us. We still have, I think, 30 seconds or so, so we are good on time, and the slide will come in.
Yeah, thank you, Piri. Good morning, everyone. Good afternoon also, wherever you are joining from. So the presentation on behalf of my PTS colleagues, but actually the list of people who contributed behind this project is much longer than what we could put on this first slide. It's about the INSPIRE project that we have been working on over the recent years. INSPIRE stands for Integrated Software Platform for the radionuclide data review. And the implementation, well, we'll talk about the implementation in a moment. So the scope of this talk will be structured around a short introduction, then a few words about the project itself and how this has been implemented, and then the key features rather very quickly, and then a summary. So the INSPIRE is one of the projects that we have been working on over the recent years within a bigger framework which aims at completing the migration to open source, moving to modern programming technologies, but also unifying the tools between particulates and noble gas. And then we took this opportunity for further optimizing the software cycle management, introducing more modularity, and being able to introduce and cope with the new technologies at the IMS, but also in terms of analysis algorithms. And INSPIRE has been implemented in 2 phases. Phase 1 was for the beta-gamma coincidence noble gas technology, and that has been delivered into IDC operation, but also to national data centers as part of NDC in a box already 2 years ago, or a bit more. And in the meantime, we completed the development by extending the functionality to high-purity germanium systems, which include both particulates and the current SPALAX technology. So this is now the picture how things look like with the current tools. We have been using INSPIRE only for beta gamma and noble gas, and in parallel we have been operating SnT2, which is a MATLAB-based application in the IDC, and Open Spectra in the NDC box. And with the new INSPIRE, with the completion of phase 2 of INSPIRE project, it will be only one unique integrated platform for both particulates and noble gas, all technologies, current and next generation, with this forward compatibility of the tool. We expect that there will be almost no need for integrating upcoming technologies. And this will be the same in both IDC and NDC box. In other words, with this new version of INSPIRE, the NDC box for RN will be exactly the same, 100% identical to the IDC pipeline. Now, what INSPIRE is doing, how this is integrated into the RN pipeline, it is used for the interactive review in routine mode by analysts, and this is produced in the reviewed report, RRR, but it is also providing the potential for producing URR, and URR is not produced in routine mode, but only on request. And this is what INSPIRE can produce for both noble gas and particulates. It's actually another business case that we addressed within this big scope of the INSPIRE, but also Autostrada that we see there, project, Grand Sim, RN Toolkit, and so on. But the focus today is only on INSPIRE. So the new version, for those of you who are familiar, is that now on the same window, you will have the list of particulates, beta gamma, noble gas, high purity germanium, noble gas. So that analysts, IDC analysts, will not need to switch forth and back from INSPIRE and SnT2, depending on whether they have to review particulates or noble gas. The same for NDC box. So it's the same one shop stop. Now, more concretely speaking, here is it's like a versatile tool which accommodates what needs to be shown and the way this needs to be displayed and made available to the analyst, depending on the technology. This is now a screenshot for a beta gamma coincidence noble gas data, and this is now for a particulate, and it's the same tool. And then number 3 is now, this is for a noble gas, but a noble gas using high purity germanium detection system. So the analysts don't need to care about how all this is happening, because we have a good mechanics behind and making all this happen very smoothly. And of course, the software allows to monitor the data quality. It's like a dashboard, traffic light like based color mapping scheme. We have green, yellow, red, depending on the quality, and this is available for the different technologies. It also offers unique possibilities for checking and updating the calibrations for all the technologies. It is also allowing to browse the peaks for particulates, but also high purity germanium, SPALAX, noble gas. This is now like a system decision support system, which allows analysts to check the peak identity, either based on the nuclide library, but it also offers the possibility to check against Monte Carlo parameters, which helps like improving the peak identification. Well, it's already good in automatic mode. The analysts will have the option to also deconvolve the peaks if needed and improve the baseline. And there is also possibilities to proceed with to perform interactive reprocessing by adjusting required parameters, and this is offered for all technologies. And then this is now a link to the nuclide library. This is also very useful for analysts to interactively browse the database for the nuclear data. And then, almost last but not least, with the same window, you can release and produce RRR or URR, depending on whether you are in routine mode or in expert analysis mode. And the RRR, these are screenshots for RRR in 3 different formats: ASCII, HTML, and XML. It's also one of the modules that we unified between particulates and noble gas. So last slide as a summary. So in short, we finished what we started a few years ago. The new version handles both noble gas and particulates. It provides very useful features and dedicated functionalities for performing the whole chains of actions that are involved in the interactive review work. It allows to perform special studies and produce the URR if there is a request. And in addition, of course, the software is handling all data types. In terms of current status, the software phase 2 is now under official pre-release testing by IDC Analysts, and it will be promoted to IDC operation, but also delivered to NDCs. NDCs already have the first version, but now they will have the new one as soon as the testing is officially completed. Of course, if there are issues, they need to be addressed before releasing this officially. So that's all I have. Thank you.
Thank you, Dr. Gheddou. So I will open the room for questions. Is there any question from the live audience or from the online audience? If you have a question, please show your hand, and then we can have an assistant that will bring you a microphone. So while we wait for this, I will maybe just ask myself a question. So where do you see the future now that we have all of these tools in an operational status? What is the next steps? Are the next steps? Are you satisfied with it? Is there a re-engineering plan like we have for SHI? What is the next?
I think in terms of re-engineering, compared to the initial objectives, we are now standing where we were hoping to be a few years ago. So we completely modernized it. And I never used the word re-engineering, but what we did is actually completely re-engineering the radionuclide pipeline. Thank you to the nice teamwork, not only internally at the level of the IDC, IMS, all PTS divisions, but also the strong support, but also the wonderful, valuable feedback that we have been getting from NDCs. It's thanks to everyone that we could make this happen.
Can you wait for the microphone, because like this the online audience can hear you? Thank you.
Okay. So I'm speaking on behalf of the analysts now from the IDC. So we expect that we'll have that soon in operation, following the procedures. And I cross my fingers for that, because this, for my understanding, is a very powerful tool that needs to be implemented there, and in order to make the life of the analyst easy in terms of analyzing the data. So that I expect that very soon coming for us. Thank you so much.
Thank you. Thank you, Jean.
There's a question on the left there. Yeah.
Thank you, Hakim. First of all, I'd like to say personally thank you for all your work you've done in pushing all of these things through. The software pipeline has continually gotten better year after year, and much thanks to your leadership. My technical question is, what is the underlying algorithms under Inspire for particulate? Is it the same algorithms as SnT2 or OpenSpectra? Or what's the underlying algorithms for that, for peak finding, things like that?
Yeah, thank you, Judah, for the support, but also nice words, but also for the question. So for the time being, the new version is, of course, offering more features compared to SnT2 and OpenSpectra. For instance, like a simple example, if there is a gain shift with the current tools, we have no way to automatically adjust the calibration. But with Inspire, we have the option to recalibrate either based on the quality control spectra or based on sample spectra themselves. And this works like with a one click. It is also offering the option to check peak identification based on Monte Carlo simulated isotope response function, which we don't have with the current tools. And so forth and so on. Well, I can maybe extend, but it's indeed a lot of new features that we have with the current tool compared to the existing ones. No.
Is there one last question from the audience? I have one last question. I don't want you to think that we never talk with each other in between SHI and radionuclide, but it's a little bit the case. I'm just wondering, what is the status with NDC in the box? Because you have all these nice tools that are ready for operations, and the synchronization with NDC in the box of all the tools. So are the member states having the same tools available that you have in the IDC?
Yeah. Yes, the NDCs have been having the same tools apart from the review tool for particulates, because SnT2 is MATLAB based. And then we could not distribute it because it should be license free, one of the requirements for NDC in the box. And that's why we worked on OpenSpectra since the very beginning, which is Java. And well, it has basically the same features than SnT2. But with this new version of Inspire, it will be again 100% the same than the IDC software. We also worked and enhanced the formats in terms of delivering the software from the initial way of providing instructions, like 200 instructions. Then we moved to virtual machine. From virtual machine, we added the RPM format, but also building from the source. And in the future, one of the things that will be good to consider is to integrate the RPM creation as part of the GitLab CI/CD within this continuous development, continuous delivery or deployment. And then NDCs will be notified automatically as soon as there is a new change in the IDC software, and this will be reflected in updated RPM that they can install very quickly on their system. That's what I think part of what the future could be made of in this area.
Thank you very much, Dr. Gheddou. So thank you for your work again. Thank you. So we will now move on to a different side of the work of the IDC with SHI technologies, and I invite Dr. Haijun Wang to the lectern for your presentation, please, and we will hear a little bit about what our team of expert analysts are doing to make sure that the bulletin that you, member state, have is really complete. The presentation is about to arrive.
So I'm waiting for the slider?
Yeah. It's coming. It will be there. On this one. On this one.
Okay. Okay. Good morning, everyone. And my name is Haijun. I'm from Data and Software RDC-MD. And my presentation is analysis and insights on manually added events by RDC analysts in the reviewed event process. Before I get started, I'd like to take this opportunity to thank the support from Mr. Gerard, and who is the section chief of RDC-MD. I also want to thank my colleagues, Paulina, Marcela, Christophe, Wolfgang, and Alessandra for there are many more good ideas and feedback on this work. And also the special thanks to Mr. Joseph, who is the Senior Evaluation Officer of PTS, for his very helpful discussion and comments for this work. So next slide, please. Okay. Okay, great. Thank you. And in this presentation, and actually which include two different parts. The first part, and you will see very general information of statistical and parameter analysis of event added by RDC analyst. The second part, I will give you one particular example and on this issue. As you know, RDC analyst analyze data based on the output from automatic data processing, which is CEST, and we will check each CEST event to reject box event, save real event in the first pass. After that, and we will take time to build event missed in CEST by scanner. All events saved by RDC analyst are LEB events. Those events added manually in LEB are what we are interested about in this presentation. And the purpose of this work is we try to have more information about those events added manually. And for instance, and if some event missed from particular error, and for analyst, we want to know why this event missed from there, and is there any specific station can be used to locate event like this, and also how big of those events. And we want to find some useful information from this work, and which can be used and for our analyst and to find some missed event from particular error. And the goal is to keep the high quality of revealed event bulletin. And actually in this work, the key is how to identify event added by analyst. Actually, it's quite simple. If you compare EVRD of a CEST event and the LEB event in RDC database, because each event will be assigned a unique identification number, EVRD, in database. And in order to make this work more convenient, and we develop a separate database in MySQL, and all those data added by analyst, we will query from RDC Arc database and copy to this separate database. And also we have some script built in Python, MATLAB, as well as SQL, and for statistical and parameter analysis. And in general, and you can see actually all those events added manually by analyst, we can find anywhere on the Earth. And around 27% of LEB events are added manually. And the magnitude is around MB 3.5. And 90% of those events added manually. The number of associated or contributed stations is less than 8. So which means most of those events are smaller events. And more information is the number of added events by analysts is per day is around 36. To double check and this work by compare EVRD, we also use BooCMP and to compare CEST bulletin and LEB bulletin. And as you know, BooCMP is a software package to compare two different bulletins to find the match event, missed event, as well as extra event. If we use a CEST bulletin as a reference bulletin, LEB bulletin is an assessed bulletin. And here you can see, and if you check the magnitude distribution and event location on the map, and all those extra events, actually this is the same event added manually, and by RDC analyst, we have quite similar and results, and by what we did by compare EVRD, except the number of event added a little bit higher by compare with EVRD. On this slide, I will give you one particular example. This event was missed in CEST and located by one of our leaders by coincidence. And here you can see magnitude of this event is MB 4.4, and we have 9 IMS seismic station used to locate this event. So definitely this is a REP events. And if you check and the waveform and on contributed station, you can see and the signal is very clear. And if you check the contributing station on the map, and we have some station in the regional distance, we also have some station in very far and to this area, and you can see. So when we talk about this event, and the first thing and coming to my mind is, so we needed to know the detection probability of those contributing stations. And so to do this, and we collect more than 4,000 IDC LEB event from ARCA database. And the event origin time started from beginning of 2010 to end of 2020. And from the magnitude distribution, you can see we have events start from very small event. We also have a very large event. And all those events we select is try to make sure those LEB event is close to the event missed in this area for our statistic of detection probability. And this is the output of the detection probability of those contributing stations. And here you can see we do have 3 stations, and it has a little bit higher detection probability, which include 2 stations in the regional distance, and also have one. The third one is very far to this area. And from this and the result, so we can see, and if we have event from there, so currently we should have at least 3 seismic stations have detections. So this is one of the very important results from this work. And because this event was missed in cell 3, so that's I'm seeing as this event was still missed in cell 1 or cell 2. And fortunately, and you can see actually this event was built in cell 1. But unfortunately, which was disappeared in cell 2. In cell 3, I don't know what is the reason. But if you check the contributed station in cell 1, and which include 4 seismic stations, and 4 of them, and there are 3 stations, and the ZLV, LPZ, and the PLC, 3 of stations is very consistent to what we did and from the previous slider, because this station, so because those station and is what we expected should find event from there. Just try to go to the previous slider. Yeah, how to? Oh, sorry. Thank you. You can see if you check the contributed station for cell 1 event, and we have 3 stations, and they build this event. If you check what we did from calculation of detection probability, we have 3 stations, has very good detection probability for event from there. So this is what we expected from this work. And the other thing, because this event was missed in cell 3, so for analysts, so I'm asking myself, and is there any automatic detection on those contributing stations? And if you check more detail from the product of automatic data processing, we do have automatic detection on those contributing stations. But the problem is the first name is not correct except 1 station. So this is, I think, is a second very important conclusion from a study of this particular events. And we also have some very roughly statistical for first name of those automatic detection and for those stations in the regional distance. And here you can see we have 2 stations, and on around 90% of detection we have the correct first name, but for LPZ, only 7% of first name of automatic detection is correct. So which means for those stations, if we have a good detection, but unfortunately the first name is not correct in automatic data processing. So for this event, we have very good, conclusion of our analyst. If we have an event missed from there, we need to double check the closest station in the regional distance. In most cases, we can have the detections, but maybe the first name is not correct. So we need to rename first name, try to build this event. If we have only 2 stations, it's better to find the detection from very far station. For instance, from this study, it's better to find the co-phase from the LOV, Cook, or McKenzie. And if you're lucky, maybe you can build event from there or can improve event from there. And this slide, I just try to give you more information, try to explain why event is very easier to miss from this error. And this is actually a snapshot of a threshold monitor. And the left side is a snapshot of threshold monitor in this day, the event missed. And the right side is a snapshot of threshold monitor in beginning of this month. And if you compare to other places, so you will find, and in this error, and the threshold monitor is a little bit higher. So which maybe can explain why event is very easier missed from there. I think probably reason maybe there is no seismic area, and the other reason maybe if we have most of our 3 component station, and the detection probability is not very high as I expected. In my conclusion, and around 27% of LEB events are added manually by analysts, and most of them are small events, and those, if you compare 2 bulletins, CEST bulletin and the LEB bulletin in both CMP, we can have almost the similar and the results. And obviously, all those manually added events are contribution from RDC analysts and to maintain high quality of RDC reviewed event bulletin. And from this particular events, we also have very important and tips or hit can be used for analysts and to find the possible event missed from there or to improve event, and we found from there. So this is what I want to present today. Thanks for your attention. With that, I'm happy to take your question. Thank you.
Thank you, Dr. Wang. Is there any question from the room? We have time for one question. I'm sure there's a lot of questions. So maybe I didn't catch it or I missed it because there were a lot of content on the slide. I didn't catch if it's already used operationally or if it's, are you already using it to add events to the REB currently, or is it something that you do later on to see what potentially was not added and should be added?
You mean the software person or?
I mean the method that you presented to us, is it something that is already operational today, that you are already using for?
Not yet. This is just and to work on this system used for this SnT. Yeah, not operational.
But it's a goal. Is it a goal?
Yeah. Thank you.
Very good. Then, thank you very much again.
Thank you.
So we will move on to the final presentation of the session, which will be given by Dr. Kunkle. And here it's a nice way of bringing those 2 first presentations together by discussing the fusion. So we will just need 1 minute to bring on the slides, and then we'll be ready for you.
Okay, thank you. So yeah, as Pierre said, I'm Josh, and I'll tell you about the Data Fusion Automatic Processing Pipeline at CTBTO. And this is a project that was started by Noriyuki, and so I've taken over that from him and described what we're doing there. So as you guys know, we have the International Monitoring System. I won't go through it in detail, but we have stations of seismic stations, hydroacoustic stations, infrasound stations, and radionuclide stations. And the idea of data fusion is to bring all of them together to provide the most comprehensive view of any event from all the technologies. So just a schematic view of the data processing. We have our 4 technologies: seismic, infrasound, hydroacoustic, and radionuclide, which have their own station processing. And then we have a global association that includes our 3 SHI technologies. And of course, radionuclide currently isn't included in that, let's say, in that data fusion. And then we also have noted at the bottom, the atmospheric transport modeling, which enhances our radionuclide reports, so the ARR and the RRR. And then for all cases, we have the analyst review. And in the SHI case, we have the LEB, then the REB, and eventually the SSEB, the standard screened event bulletin, which intends to include events that we cannot rule out as being seismic. So the idea of data fusion then is to take these products, the SSEB, the RRR, along with the atmospheric transport modeling, to try to bring those together to say which events measured by radionuclide stations are related to which seismic events which appear in the standard screen event bulletin. And from this, the idea is to make a new, let's say, product of fused events that can be further analyzed. So just to give you the perspective, so we have our waveform side, our SHI side, where we take data from multiple stations. So we have waveforms from our hydro, infrasound, and seismic technologies. And in the end, we produce an ellipse. So we have a point which is let's say the best location of the event, and an error ellipse which indicates the uncertainty in that location. And in the radionuclide side, okay, it's a different idea. We have some spectra from which we determine some nuclides, which we quantify the nuclides of interest. There are some naturally occurring nuclides, which you see all the time, and then of course we have more the level 4, level 5 anthropogenic cases. And so from data fusion, we have to bring these two together, and of course, like I said, we use the atmospheric transport modeling to do that. And so this provides our connection. So I show a figure here, two figures from WebGrape. So this is showing an SRS field from the Swedish station, and you can see there it's a backward ATM simulation. So what it does is it propagates passive tracers through the atmosphere based on our wind field data. Normally you would think that this goes forward in time, which we also do, but our standard product is to do it backwards in time. So you start from the station, go backwards in time, and ask what could have produced a signal at that station. And so you see in this figure here, you have 10 hours, which is sort of near the station because only something near the station would have reached there in 10 hours. And then as you expand time, you cover more and more area, and you see where, for example, 115 hours ago that signal might have come from. And so these are our source receptor sensitivity fields. They go backwards in time for 14 days. And with a current resolution of 1 hour in time and half a degree in latitude and longitude. So quite a lot of data there. So what do we do? We have a hypothetical SHI ellipse here that I've drawn on the map, and we want to ask, okay, is there an overlap between our SRS field and our SHI event? And of course, the SHI events, they can be, let's say, well located, or they can have larger, the ellipse size can be small or large, depending on how well they're located. And so we consider the overlap of the SRS with any of the, which is shown in the boxes there with the SHI ellipse. So we consider all cells that are overlapping. And if that happens, we count that as a fusion result. And this results in a many-to-many relationship between the RN samples and the waveform events. So a single RN sample will match multiple waveform events, and a single waveform event may match multiple RN samples. And we should see this as the maximal set of possible matches, which we then need to further process and understand, because it doesn't tell you that an event of interest has happened. It just tells you what could be related. So to help the visualization here, instead of showing these maps of time snapshots, what we can do is we can emphasize the time dimension by throwing away one spatial dimension. So that's what this figure on the right here is. So I projected out the longitude, so on the x-axis we're looking at latitude, and on the y-axis is time. So at the very top is the station at time 0 and at its location, and then you see the SRS field going through time, backwards through time. And the reason why I want to show this is because we can then talk about how we consider our SHI events. Because we don't just consider an event happening at a certain time, but we need to account for delayed release. So that means even though if there's a real underground nuclear test, we know from past experience, for example, by the DPRK test in 2013, that actually the radionuclides may stay contained until they're released later. And in that case, it was something like 50 days until the release happened. So in data fusion, we consider a delayed release of up to 60 days. And you see this on the figure. I've shown you, at the bottom is our SHI event. So here it's sort of a point. And instead of just considering the overlap at that point, we then release the time constraint, and it considers overlaps for the whole time up to 60 days. And so then instead of having a single SRS value at the time, you have a time series. And that's what this figure on the left is showing. So this is the prediction from the full 2D SRS field. So you see that it's not always overlapping. But the idea is you have instead of one value at a prompt time, you have a time series. And so now we need to further use that to understand what's going on. So this also presents additional challenges. So in the figure here, I'm showing the release delay. So at 0, it's prompt. And on the y-axis is the average number of fused events, so the average number of fused results. And this is looking over the year of 2021. And so if it's a prompt release, you have a handful, which is fine. As soon as you start increasing the fusion time up to 60, you get hundreds and hundreds of matches, which makes it essentially impossible to analyze that from an expert point of view. And so if we want to have an expert look at fusion results and be able to give input on, okay, what could have caused it, or any more information about it, we need to now take this information and give some ranking or filtering that can be utilized. And one way to do that is to take information from multiple stations. So then that brings me to the future work. So on the figure I'm showing, I took the same traces we saw before, but now actually considering additional stations. And you see that in this trace of SRS values, in some cases the stations, let's say, agree that there may be a contribution there, and in some cases they don't agree. And so this is the idea of including, let's say, positive and negative information in constraining our results. And so if we really want to consider it as being a real event, then all the stations that should see the event should agree on the time of the release and should also agree on the actual measurement. And so the next steps is, first, we want to investigate a probabilistic model which can help incorporate these non-detections. And this has been a big point of discussion here at the whole conference. It's been very fruitful discussion. And so that's a good motivation to go in this direction. So if we have a probability model, we bring in both detects and non-detects. It can help constrain what we're fusing. And also, then we can also move to looking at Bayesian inference, such as the freer software package, which we've heard a lot about also at this conference. So those are the next ideas for data fusion and how to bring our wide set of fused events down to something that can be further analyzed by experts, and we'll go from there. Thank you.
Thanks a lot. So is there, I think we have a bit of time, so is there any questions for the author? Yeah, there is one. Can I have a microphone, please, for the audience live online?
Thank you. It was very interesting. You mentioned that you still are going backward as always, and my question is about this basic philosophy. The delayed, the possible delayed time between the wave signals and the radionuclide, you mentioned that it can create a lot of possible attributions. Since we're talking about data fusion, have you considered another different philosophy where the wave signals might be considered like posing a question, and then you look forward and look for possible answer in the radionuclide signals to see if there's a match that can be attributed to such a wave signal at the beginning?
Mm-hmm. Oh, I don't have the slides. So I sort of hinted at that in one of the slides, that actually what we have in our current fusion portal, which you can see on the secure web portal, we have fusion from a radionuclides perspective and fusion from a waveform perspective. So in that sense, you can go and say, okay, I'm interested in this radionuclide event, and then display all the fused waveform events. On the other hand, you can say, I'm interested in this waveform event, and display all of the fused radionuclide events. So we have it from those two perspectives. So we're trying to approach it from both ways. So I hope that. The ATM simulation. Because we have the standard backward simulation, we utilize that. But the idea is that if you were to say, to make a forward simulation at an SHI event, and then ask sometime in the future what that SRS value at the station is, you should get the same result from the backward simulation if you backward simulate from the station to the SHI event. So I think that's the methodology in our ATM. In theory, we could, because now we're doing a backwards ATM simulation for every station, for both particulate and noble gas. So it's something like 160 per day. I think that's right. So actually, on average, the number of LEB events is similar. So you could consider instead doing forward simulations, but then that's also depends on seismicity, and so it wouldn't be stable. So the idea is we do the backward simulation and rely on the fact that we should get the same information from the backward simulation as we do for the forward. But that's something to look more to understand better too.
If you wanted to illustrate something, sorry, we only have the slides now. But
Oh, it's okay, yeah.
It's okay? Okay. Is there one final question for the speaker? Everybody's satisfied. Thanks a lot. It was great.
Thanks.